The ℜ bias strip or ℜ bias band, also Mobius or Moebius, is a surface with only one side and only one boundary component. The ℜ bias strip has the mathematical property of being non-orientable. It can be realized as a ruled surface. It was discovered independently by the German mathematicians August Ferdinand ℜ and Johann Benedict listing in 1858. A model can easily be created by taking a paper strip and giving it a half twist, and then joining the ends of the strip together to form a loop. In Euclidean space there are two types of ℜ bias strips depending on the direction of the half twist, clockwise and counterclockwise. That is to say, it is a chiral object with handedness. The ℜ bias strip is not a surface of only one geometry, such as the half-twisted paper strip depicted in the illustration to the right. Rather, mathematicians refer to the ℜ bias band as any surface that is homeomorphic to this strip. Its boundary is a simple closed curve, that is, homeomorphic to a circle. This allows for a very wide variety of geometric versions of the ℜ bias band as surfaces each having a definite size and shape. For example, any closed rectangle with length L and width W can be glued to itself to make a ℜ bias band. Some of these can be smoothly modeled in three-dimensional space, and others cannot. Yet another example is the complete open ℜ bias band. Topologically, this is slightly different from the more usual closed ℜ bias band, in that any open ℜ bias band has no boundary. It is straightforward to find algebraic equations the solutions of which have the topology of a ℜ bias strip, but in general these equations do not describe the same geometric shape that one gets from the twisted paper model described above. In particular, the twisted paper model is a developable surface. A system of differential algebraic equations that describes models of this type was published in 2007 together with its numerical solution. The Euler characteristic of the ℜ bias strip is 0. Properties. The ℜ bias strip has several curious properties. A line drawn starting from the seam down the middle will meet back at the seam but at the other side. If continued, the line will meet the starting point and will be double the length of the original strip. This single continuous curve demonstrates that the ℜ bias strip has only one boundary. Cutting a ℜ bias strip along the center line with a pair of scissors yields one long strip with two full twists in it, rather than two separate strips. The result is not a ℜ bias strip. This happens because the original strip only has one edge that is twice as long as the original strip. Cutting creates a second independent edge, half of which was on each side of the scissors. Cutting this new, longer, strip down the middle creates two strips wound around each other, each with two full twists. If the strip is cut along about a third of the way in from the edge, it creates two strips. One is a thinner ℜ bias strip it is the center third of the original strip, comprising 1/3 of the width and the same length as the original strip. The other is a longer but thin strip with two full twists in it this is a neighborhood of the edge of the original strip, and it comprises 1/3 of the width and twice the length of the original strip. Other analogous strips can be obtained by similarly joining strips with two or more half-twists in them instead of one. For example, a strip with 3 half-twists, when divided lengthwise, becomes a strip tied in a trefoil knot. A strip with n half-twists, when bisected, becomes a strip with n plus 1 full twists. Giving it extra twists and reconnecting the ends produces figures called palindromic rings. A strip with an odd number of half-twists, such as the ℜ bias strip, will have only one surface and one boundary. A strip twisted an even number of times will have two surfaces and two boundaries. If a strip with an odd number of half-twists is cut in half along its length, it will result in a single, longer strip, with twice as many half-twists as in the original plus two more. Alternatively, if a strip with an even number of half-twists is cut in half along its length, it will result in two linked strips, each with the same number of twists as the original. Geometry and topology. One way to represent the ℜ bias strip as a subset of R3 is using the parametrization. where 0 per mil currency U less than 2 I euro and a 1 per mil currency VA per mil 1 currency. This creates a ℝ paragraph bias strip of width 1 whose center circle has radius 1, lies in the xy plane and is centered at. The parameter U runs around the strip while V moves from one edge to the other. In cylindrical polar coordinates, an unbounded version of the ℝ paragraph bias strip can be represented by the equation. Fattest rectangular ℝ paragraph bias strip in 3 space, if a smooth ℝ paragraph bias strip in 3 space is a rectangular euro that is created from identifying two opposite sides of a geometrical rectangle euro, then it is known to be possible if the aspect ratio of the rectangle is greater than the square root of 3. For an aspect ratio less than or equal to the square root of 3, however, a smooth embedding of a rectangular ℝ paragraph bias strip into 3 space may be impossible. As the aspect ratio approaches the limiting ratio from above, any such rectangular ℝ paragraph bias strip in 3 space seems to approach a shape that in the limit can be thought of as a strip of 3 equilateral triangles, folded on top of one another so that they occupy just one equilateral triangle in 3 space. If the ℝ paragraph bias strip in 3 space is only once continuously differentiable, however, then the theorem of Nash-Cooper showed that there is no lower bound. A method of making a ℝ paragraph bias strip from a rectangular strip too wide to be simply twisted and joined is to first fold the wide direction back and forth using an even number of folds an accordion fold so that the folded strip becomes narrow enough that it can be twisted and joined, much as a single long enough strip can be joined. With 2 folds, for example, a 1A, one strip would become a 1za folded strip whose cross-section is in the shape of an N and which would remain an N after a half twist. This folded strip, 3 times as long as it is wide, would be long enough to then join at the ends. This method works in principle but becomes impractical after sufficiently many folds, if paper is used. Using normal paper, this construction can be folded flat, with all the layers of the paper in a single plane. But mathematically, it is not clear whether this is possible without stretching the surface of the rectangle. Topology. Topologically, the ℝ paragraph bias strip can be defined as the square, 0, 1, 0, 1, with its top and bottom sides identified by the relation for 0 per mil currency xa per mil 1 currency, as in the diagram on the right. A less used presentation of the ℝ paragraph bias strip is as the topological quotient of a torus. A torus can be constructed as the square, 0, 1, 0, 1, with the edges identified as and. If 1 then also identified, then 1 obtains the ℝ paragraph bias strip. The diagonal of the square where both coordinates agree, becomes the boundary of the ℝ paragraph bias strip, and carries an or bifold structure, which geometrically corresponds to reflection geodesics in the ℝ paragraph bias strip reflect off the edge back into the strip. Notationally, this is written as T2 per second 2 the 2 torus quotiented by the group action of the symmetric group on 2 letters, and it can be thought of as the configuration space of 2 unordered points on the circle, possibly the same, with the torus corresponding to 2 ordered points on the circle. The ℝ paragraph bias strip is a 2-dimensional compact manifold with boundary. It is a standard example of a surface which is not orientable. In fact, the ℝ paragraph bias strip is the epitome of the topological phenomenon of non-orientability. This is because 1, 2-dimensional shapes are the lowest dimensional shapes for which non-orientability is possible, and 2, the ℝ paragraph bias strip is the only surface that is topologically a subspace of every non-orientable surface. As a result, any surface is non-orientable if and only if it contains a ℝ paragraph bias band as a subspace. The ℝ paragraph bias strip is also a standard example used to illustrate the mathematical concept of a fiber bundle. Specifically, it is a non-trivial bundle over the circle S1 with a fiber the unit interval, I equals 0, 1. Looking only at the edge of the ℝ paragraph bias strip gives a non-trivial 2-point bundle over S1. Computer graphics. A simple construction of the ℝ paragraph bias strip which can be used to portray it in computer graphics or modeling packages is as follows. Take a rectangular strip. rotate it around a fixed point not in its plane. At every step also rotate the strip along a line in its plane and perpendicular to the main orbital radius. The surface generated on one complete revolution is the ⁻bias strip. Take a ⁻bias strip and cut it along the middle of the strip. This will form a new strip, which is a rectangle joined by rotating one end a whole turn. By cutting it down the middle again, this forms two interlocking whole turn strips. Open ⁻bias band. The open ⁻bias band is formed by deleting the boundary of the standard ⁻bias band. It is constructed from the set S equals O to a 0 per mole currency x A per mole 1 currency and 0, y less than 1 by identifying the points and for all 0, y less than 1. It may be constructed as a surface of constant positive, negative, or zero curvature. In the cases of negative and zero curvature, the ⁻bias band can be constructed as a complete surface, which means that all geodesics may be extended indefinitely in either direction. Constant negative curvature, like the plane in the open cylinder, the open ⁻bias band admits not only a complete metric of constant curvature 0, but also a complete metric of constant negative curvature, say equals -1. One way to see this is to begin with the upper half-plane model of the hyperbolic planar, namely a equals, x, y, a2y greater than 0 with the Riemannian metric given by /y2. The orientation-preserving isometries of this metric are all the maps f, a of the form f, z, a equals /, where a, b, c, d are real numbers satisfying AD, bc equals 1. Here z is a complex number with z, 0, and we have identified a with z z, 0 endowed with a Riemannian metric that was mentioned. Then one orientation reversing isometry G of a given by G, Z, A equals conj, Z, where conj, Z, denotes the complex conjugate of Z. These facts imply that the mapping H, A given by H, Z, A equals -2 a conj, Z, is an orientation reversing isometry of A that generates an infinite cyclic group G of isometries. The quotient /G of the action of this group can easily be seen to be topologically a ⁻bias band. But it is also easy to verify that it is complete and non-compact, with constant negative curvature equals -1. The group of isometries of this ⁻bias band is one-dimensional and is isomorphic to the circle group SO, 2. Constant, zero curvature. This may also be constructed as a complete surface, by starting with portion of the planar 2 defined by 0 per mole currency y per mole 1 currency and identifying with for all x in R. The resulting metric makes the open ⁻bias band into a complete flat surface. This is the only metric on the ⁻bias band, up to uniform scaling, that is both flat and complete. The group of isometries of this ⁻bias band is one-dimensional and is isomorphic to the circle group SO, 2. Constant positive curvature. A ⁻bias band of constant positive curvature cannot be complete, since it is known that the only complete surfaces of constant positive curvature are the sphere and the projective plane. The projective plane P2 of constant curvature equals 1 may be constructed as the quotient of the unit sphere S2 in A3 by the antipodal map A, S2 a S2, defined by A, X, Y, Z, equals. The open ⁻bias band is homeomorphic to the once punctured projective plane, that is, P2 with any one point removed. This may be thought of as the closest that a ⁻bias band of constant positive curvature can get to being a complete surface, just 1 point away. The group of isometries of this ⁻bias band is also one-dimensional and isomorphic to the circle group SO, 2. The space of unoriented lines in the plane is diffeomorphic to the open ⁻bias band. To see why, let L, I, denote the line through the origin at an angle I to the positive x-axis. For each L, I, there is the family P, I, of all lines in the plane that are perpendicular to L, I. Topologically, the family P, I, is just a line intersects the line L, I, in just one point. In this way, as I increases in the range 0 a degree a per mole currency I 180 a degree, the line L, I, represents a line's worth of distinct lines in the plane. But when I reaches 180 a degree, L, 180 a degree is identical to L, 0, and so the families P, 0 a degree and P, 180 a degree of perpendicular lines are also identical families. The line L, 0 a degree, however, has returned to itself as L, 180 a degree pointed in the opposite direction. Every line in the plane corresponds to exactly one line in some family P, I, for exactly one I, for 0 a degree a per mole currency I 180 a degree, and P, 180 a degree is identical to P, 0 a degree but returns pointed in the opposite direction. This ensures that the space of all lines in the plane are the union of all the L, I, for 0 a degree a per mole currency I a per mole 180 currency a degree a is an open ℝ paragraph bias band. The group of bijective linear transformations GL, 2, R, of the plane to itself naturally induces bijections of the space of lines in the plane to itself, which form a group of self-homeomorphisms of the space of lines. Hence the same group forms a group of self-homeomorphisms of the ℝ paragraph bias band described in the previous paragraph. But there is no metric on the space of lines in the plane which is invariant under the action of this group of homeomorphisms. In this sense the space of lines in the plane has no natural metric on it. This means that the ℝ paragraph bias band possesses a natural four-dimensional Lie group of self-homeomorphisms, given by GL, 2, R, but this high degree of symmetry cannot be exhibited as the group of isometries of any metric. ℝ paragraph bias band with round boundary, the edge, or boundary, of a ℝ paragraph bias strip is homeomorphic to a circle. Under the usual embeddings of the strip in Euclidean space, as above, the boundary is not a round circle. However, it is possible to embed a ℝ paragraph bias strip in 3 dimensions so that the boundary is a perfect circle lying in some plane. For example, see figures 307, 308, and 309 of Geometry in the Imagination. A much more geometric embedding begins with a minimal Klein bottle immersed in the 3-sphere, as discovered by Blaine-Lawson. We then take half of this Klein bottle to get a ℝ paragraph bias band embedded in the 3-sphere. The result is sometimes called the Sudanese ℝ paragraph bias band. Here Sudanese is a portmanteau of the names of 2 topologists, Sue Goodman and Daniel Asimov. Applying stereographic projection to the Sudanese band places it in 3-dimensional space, as can be seen below. A version due to George Francis can be found here. From Lawson's minimal Klein bottle we derive an embedding of the band into the 3-sphere S3, regarded as a subset of C2, which is geometrically the same as R4. We map angles to complex numbers via. Here the parameter I runs from 0 to I and I runs from 0 to 2 I. Since a Z1 a €2 plus a Z2 a €2 equals 1 the embedded surface lies entirely in S3. The boundary of the strip is given by a Z2 a equals 1, which is clearly a circle on the 3-sphere. To obtain an embedding of the ℝ paragraph bias strip in R3 one maps S3 to R3 via a stereographic projection. The projection point can be any point on S3 which does not lie on the embedded ℝ paragraph bias strip. One possible choice is stereographic projections map circles to circles and will preserve the circular boundary of the strip. The result is a smooth embedding of the ℝ paragraph bias strip into R3 with a circular edge and no self-intersections. The Sudanese ℝ paragraph bias band in the 3-sphere S3 is geometrically a fiber bundle over a great circle, whose fibers are great semicircles. The most symmetrical image of a stereographic projection of this band into R3 is obtained by using a projection point that lies on that great circle that runs through the midpoint of each of the semicircles. Each choice of such a projection point results in an image that is congruent to any other. But because such a projection point lies on the ℝ paragraph bias band itself, 2 aspects of the image are significantly different from the case where the point is not on the band. 1. The image in R3 is not the full ℝ paragraph bias band, but rather the band with one point removed. And 2, the image is unbounded and as it gets increasingly far from the origin of R3, it increasingly approximates a plane. Yet this version of the stereographic image has a group of 4 symmetries in R3, as compared with the bounded version illustrated above having its group of symmetries the unique group of order 2. But the most geometrically symmetrical version of all is the original Sudanese ʻmɜrbiəs band in the 3-sphere S3, where its full group of symmetries is isomorphic to the Lie group O, 2. Having an infinite cardinality, this is far larger than the symmetry group of any possible embedding of the ʻmε{bias band in A3. Related objects. A closely related strange geometrical object is the Klein bottle. A Klein bottle can be produced by gluing 2 ʻmε{bias strips together along their edges. This cannot be done in ordinary three-dimensional Euclidean space without creating self-intersections. Another closely related manifold is the real projective plane. If a circular disk is cut out of the real projective plane, what is left is a ʻmε{bias strip. Going in the other direction, if one glues a disk to a ʻmε{bias strip by identifying their boundaries, the result is the projective plane. In order to visualize this, it is helpful to deform the ʻmε{bias strip so that its boundary is an ordinary circle. The real projective plane, like the Klein bottle, cannot be embedded in 3 dimensions without self-intersections. In graph theory, the ʻmε{bias ladder is a cubic graph closely related to the ʻmε{bias strip. In 1968, Gonzalo var copyrightless Johann discovered 3-dimensional bodies with ʻmε{bian characteristics, later described by Martin Gardner as prismatic rings that became toroidal polyhedrons. Applications. There have been several technical applications for the ʻmε{bias strip. Giant ʻmε{bias strips have been used as conveyor belts that last longer because the entire surface area of the belt gets the same amount of wear, and as continuous loop recording tapes. ʻmε{bias strips are common in the manufacture of fabric computer printer and typewriter ribbons, as they allow the ribbon to be twice as wide as the print head while using both halves evenly. A ʻmε{bias resistor is an electronic circuit element that cancels its own inductive reactance. Nikola Tesla patented similar technology in 1894. Coil for electromagnets was intended for use with his system of global transmission of electricity without wires. The ʻmε{bias strip is the configuration space of 2 unordered points on a circle. Consequently, in music theory, the space of all 2-note chords, known as dyads, takes the shape of a ʻmε{bias strip. This and generalizations to more points is a significant application of all bifolds to music theory. In physics electrotechnology, as a compact resonator with a resonance frequency which is half that of identically constructed linear coils, as an inductionless resistor, as superconductors with high transition temperature, in chemistry nanotechnology, as molecular knots with special characteristics, as molecular engines, as graphene volume with new electronic characteristics, like helical magnetism, in a special type of aromaticity, ʻmε{bias aromaticity, charged particles that have been caught in the magnetic field of the Earth can move on a ʻmε{bias band. The cyclotide chelate B1, active substance of the plant Holdenlandia afnis, contains ʻmε{bias topology for the peptide backbone. Popular culture, Mobius band, an electronic rock trio from Brooklyn, New York. Through the Moebius strip, a 2000 feature film made in China. Homestuck, a weak comic which features Mobius strips as a recurring plot element and in joke. In Sonic Riders, Zero Gravity, one of the story's boss level is named after this by its shape. In Futurama, the first episode of the 10th season features a drag race on a Mobius strip. See also. References. External links, H2G2, The Amazing ʻmε{bias strip, knitted version, the ʻmε{bias gear a functional planetary gear model in which one gear is a ʻmε{bias strip, Westerstein, Eric W., ʻmε{bias strip, MathWorld. Beyond the Mobius strip, J. S. Bach's crab cannon visualized on a Mobius strip. An M.C. Escher-inspired Ma paragraph bias ring world, ZAR copyright Quinn, Carlo H. Mobius Bridges and Buildings. Brady Heron. Retrieved April 10, 2014 A.